in business critical memory intensive applications in data centers, including, for example, graph processing, which has hundreds of billions of nodes these days, and in-memory database, which stores growing data or tables into memory. Basically, memory intensive applications store these huge data sets into local memory for fast and low latency accesses. However, memory provisioning for these applications is hard, mostly because memory is limited by the server physical boundary. For example, data center operators normally over-provision or reserve memory for peak usage to avoid out-of-memory errors. This partially causes only 40 to 60% of memory utilizations in data centers. Growing application data in one OS process may even exceed single machine memory limits. So with this problem, people ask, can we just let the application dynamically utilize the unused memory on other servers? So there are a bunch of work on file memory over commodity servers that try to address this problem. From a high level, file memory could be viewed as one specific type of memory disaggregation. Here we have a cluster of commodity servers or nodes connected by data center network with 100G bandwidth and few microsecond latencies. Different nodes may host different applications. For example, node 1 runs graph processing, node 2 runs an in-memory database, and node 4 and 5 run some email services. At some moment, the memory-intensive graph processing and database applications use most of their local memory in their host nodes, while node 4 and 5 may just leave a lot of unused memory. So the file memory technique aggregates this unused memory into a file memory pool that is accessible via this fast data center network, and lets memory-intensive applications dynamically allocate this memory from the pool to store their data. So in this way, the application data center operators could dynamically provision other servers' unused memory to the memory-intensive applications, and this application can use much more memory than single machine limit. So now let's just focus on one application running on one node and using file memory pool to store its data. For brevity, we just call that node the local node, and the set of nodes that could donate file memory the remote nodes. In our work, we assume the application uses remote pointers as the interface to access file memory. So this is the same as what people did in AFM, or application integrated file memory from OSDI 20. So the basic idea is, let's first omit this dotted line. So the application holds several removable pointers, which are similar to smart pointers in C++. So these smart pointers encode some information that to locate objects that either reside in local memory or remote memory. This object also called removable objects. The system runtime will swap in or fetches any object that the application wants to access. In the background, it also try to swap out or evict some code object to the file memory. So the general idea of file memory technique sounds cool, right? However, one practical problem is, what if the remote node fails? So let's assume that the remote node 2 fails. Then the application data on that node will be lost, right? This would cause severe trouble or even crashes to the running applications on the local node. So essentially, the probability of application crash will grow almost linearly as the number of remote nodes increases. Therefore, we argue that any practical file memory system must tolerate remote node failures. So that's a main theme of this talk. How do we build a fault-tolerant file memory system? Here we assume fail stop faults and no partial network failures, because we basically assume the file memory system is normally deployed within a single cluster or even single rack with reliable networks. But even under this assumption, it is still hard to achieve efficient fault tolerance, as we will show later. So in this talk, I will first go through why we think in-memory erasure coding is a good direction to go. Then I will present how Carbink makes erasure coding work in practice for file memory systems. Finally, we will evaluate the performance and cost. two general approaches for data fault tolerance, replication or erasure coding. In the replication approach, for example, to tolerate two remote node failures, the local node could just write each piece of data into 3 remote nodes. However, doing so will incur high memory overheads. Instead, in the erasure coding approach, the local node could do something like splitting the piece of data into 4 data chunks and generate 2 parity chunks and write these 6 chunks to these different remote nodes. So erasure coding will guarantee that they can recover any lost chunks upon up to 2 node failures. So this approach has much smaller memory usage than compared to the in-memory replication. Besides this, erasure coding runs pretty fast on commodity servers, for example, 4 GB per second using single core. So therefore, considering the memory usage, we prefer erasure coding for file memory. Well, you might think that can we use SSD to store replicas or parity data for the fault tolerance? This does save memory. However, but doing so will force the application performance to bottleneck on the SSD during bursty workload or failure recovery, as shown by prior work. Memory fault tolerance for file memory. Great, I just talked about in-memory erasure coding has the benefits of high performance and low memory usage. Next, I'm gonna talk about how Carbink makes in-memory erasure coding work in practice for a file memory system. Specifically, we will look at 2 challenges. The first challenge is about how to handle removable objects that have different sizes. So recall that in AFM, like file memory system, the abstract application data into removable objects, just like some heap objects. So depending on the application needs, these objects normally have different sizes. However, erasure coding on irregular size object is hard. The reason because it normally requires equal size chunks to generate parity chunks. So you may do padding to align these objects, but this would waste padding space memory. You may split each object into smaller chunks equally, but doing so for small object would incur large metadata to store additionally, such as each chunk's location. So to efficiently erasure code this irregular size object, Carbink approach is to group similar size object into spans, just like how some memory allocator manage their object, for example, Google's TCmalloc. These spans are page aligned and narrow and regular sized, thus well suited for erasure coding. For example, for 1 kilobyte object, we pack 8 of them into a 8 kilobyte span. For some larger object like 3.3 kilobyte, we basically pack 7 of them into a 24 kilobyte span with small fragmentation. So the high level idea is we borrow this TCmalloc configuration to pack object into proper sized span in a way that the end of span fragmentation is minimized. We call this approach span-centric memory pooling and apply it to the object management and data swapping between the local and file memory. So basically this approach generates spans that are always page aligned and never end up with a partial object, which are easy for managing and apply erasure coding. Apply erasure coding to file memory system is how to achieve efficient swapping. A natural way of apply erasure coding is suggested in a prior work called Hydra, which is based on 4 kilobyte OS pages. In our setting, in our span context, we call it easy split. So as shown in this diagram, the high level idea is they split each span into 4 data chunks, generate 2 parity chunks, and write these to remote nodes. However, the drawback of doing so is the local nodes needs multiple network IO operations to swap in or out any single span because of the span splitting. These excessive network IO operations will stress the network stack and lead to slow swapping. It also makes the swapping or data fetch vulnerable to stragglers. For example, the straggler from the network. This would cause high tail latency for remote accesses. So with this drawback, we were thinking of can we avoid splitting spans? So this is achieved in our new approach called easy batch by erasure coding span sets. Basically, a span set is a group of equal size spans. As shown in the right diagram, we swap out a batch of 4 spans and their parity to remote nodes. Averagely, span swap out only requires 1.5 number of IO operations. During swapping, We only need single IO operation to fetch the specific span that contains the desired object. So this achieves fast swapping and low tail latency without being vulnerable to stragglers. However, since we swap in and swap out in different granularity, you might thought of this could cause some remote fragmentation. For example, in this diagram, the local node swap out span set 1, later is swapping span 1 and 2 into local memory. So because each span only lives in one place in the local file memory, this leaves two invalid span size holes in span set 1 on file memory. Similarly, it creates two invalid holes on another span set 2. These invalid holes would persist and cause file memory fragmentation because in future swap outs, EC batch will always write out new span sets. Host, EC batch runs remote compaction. In the same example, the remote compaction basically merges the remaining spans in span set 1 and 2 into a new span set 3 with new parity data, P5 and P6 in this case. This also creates a bunch of free space that comes from the host in span set 1 and 2, which can be used for later span set swap out. And additionally, during merging spans, we do not really memory copy span data. Instead, the local node maintain a span set mapping that map each span set to its spans. To merge remaining spans into new span set, we just invalidate these old mappings for old span sets and insert a new entry for this new span set. With this layer interaction, our remote compaction actually achieves zero copy span merging. So here I want to highlight that the remote compaction does not impact the span swap in and swap out performance because it's of the critical path of swap ins and outs. The only penalty is that it might consume more file memory because some dead spans might not be compacted immediately. So we'll evaluate this point later. Which adopts span-centric memory pooling to manage irregular or arbitrary size objects, and then apply erasure coding to span sets to achieve efficient swapping. Next, we're gonna evaluate the performance cost of this design. We use three types of workloads covering in-memory database transactions, graph processing, and microbenchmark studying the system sensitivity. We evaluate on various dimensions: throughput, tail latency, remote memory usage, and more. We use commodity server with 50G NICs and Pony Express user space network stack. This network stack provides us efficient one-sided RMAs for the span swapping and RPCs for the remote compaction. We first look at the throughput of this transactional key value store. As shown in this figure, the x-axis varies the size of the local memory, and y-axis varies the transaction throughput of EC split versus EC batch, both under Carbink span-centric design. So both schemes throughput increases as this local memory increases. With higher local memory, these two perform similarly because the working set is, on that case, mostly fit into local memory, including very few swaps. But with smaller local memory, our EC batch achieves up to 1.5 speed up over EC split due to less IO operations per swap. Swapping tail latency. In this figure, the x-axis is a throughput of accessing remotable objects, while y-axis shows the 99th percentile latency of these swaps, of these accesses. Overall, we found the EC batch achieved 1.2 to 1.4x tail latency reduction over EC split. This is because EC batch only need single IO operations per data fetch. More memory usage, EC batch has at most 35% of more memory usage than EC split due to remote compaction of the critical path. But this is still only 2/3 of replication memory usage. So there are more results in the paper to check it out. And to summarize in this talk, we argue that fault tolerance is a must-have feature for application to use file memory. Our system Carbink makes erasure coding based fault tolerance work in practice for file memory system by grouping objects into spans to handle arbitrary size objects and erasure coding span sets to achieve single network IO operation data fetch. As a result, it achieves up to 1.5 application speed up and 1.4x tail latency reduction at the price of bit high memory usage. Finally, in a high level, we think performance and fault tolerance are the two keys to enabling memory disaggregation, and Carbink is a step forward towards the fault-tolerant design. With this, I'm happy to take any questions. Thank you.
Any questions from the audience in the?
Thanks for the talk. It was very interesting. I know you had it as a bullet at the very end. I was just wondering if you could say a little bit more about the overhead costs of doing reconstruction of a failed server.
Oh, I see. Basically, the failure recovery if one server fails. Yeah, we had some evaluation, but the high-level result is we try to compare with the replication-based approach. Basically, the replication will have more memory usage. And for our approach, when the server fails, we need to do this erasure coding, gathering all the codes from the other nodes and rebuild a new nodes. So the recovery time will be longer. In our rough result is 1.7 more time to recover nodes. And we also measure something maybe more like relevant to the application performance drop when a node failures. Because the reason that application workload normally they have some hotness, you only need to recover this hotness in the fly, and the other access are just rare, so you can recover the rest in the background. So during the for the application slowdown during the failure, it's roughly similar to a replication. I mean, just a few. I mean, few under second level of application slowdown. Yeah. Sorry. It's mostly hidden from application. Yeah, it's mostly hidden from application.
So, do you have is there a slide? No, there's no. Okay. So, in here, and I have a question. Wondering about the performance. So, this performance is comparing to EC split, right?
Yes.
So, do you have other baselines? For example, this is all based on remotable pointers, AIFM.
Mm-hmm.
So, I'm just wondering, like, if you compare this with a swap based.
Mm-hmm.
Because they already are like 4 KB, and then they like without fault tolerance, they should run slower than AIFM, but maybe like the 4 KB pages are easier to do erasure coding, and then altogether, maybe it's still faster. So I'm just wondering if you have any comments on that. I
see. That's a good question. So so first, this job was done why internally at Google, and normally it's very hard for me to hack the operating system. So I adopt this AFM design. And so one benefit is you do not need to modify the kernel, but as you say, you need to handle like arbitrary size objects instead of regular 4 KB OS pages. So if we add in fault tolerance to this 4 KB OS pages, I would think the Carbink or like AFM type approach will still have better performance. The reason is because because the AFM or the Carbink approach, they touch this individual object. You have the ability to control what size of object you put on remote. So in our AFM work, we actually, in our Carbink work, we actually put the large object to the remote memory. So this object tend to be cold based on our trace analysis in the production. And we tend to find most of the access are in a small object in the local memory. So their performance is actually pretty good in terms of this accessing remote large objects. Yeah, but I haven't done the detailed comparison of this paging-based system, but that would be a good future work. Yeah.
Question about the performance of the Erasure coding. So you said that it has a performance of 4 GB per second, and I'm wondering if it would scale to faster NICs, if we have a 100 or 400 gigabits per second NIC, is that good enough for it? So
yeah,
I'm thinking the scaling problem is not really that easy to solve. I see.
So yeah, so I can give you a really detailed example. So I did some tests that I tried to do memory copy between just one region of memory to another region of memory within the same NUMA node. It's actually roughly achieved for small, like a 4 kilobyte like size. You can roughly achieve 6 gigabyte per second of bandwidth. But with erasure coding, what you can basically achieve like 4 gigabyte per second. So you can see the for erasure coding, the major bottleneck I would think of is the memory bandwidth. So as long as your memory bandwidth is gonna scale to this number, to the bandwidth of your NIC, I think this erasure coding will also scale. Because like you can think of one call in one server can sustain 4 gigabyte per second erasure coding. Then you have 2 call, probably you are gonna hit 8 gigabyte per second, which is good enough for 100G NIC.